Hello everyone, I hope you are doing fine. So welcome back to our last module, which is module 6, Determinants. So in this modules, we're going to cover a few things. So the first subsections that we're going to cover is determinants by perfector expansions, followed by evaluating determinants by row reductions and Kramer rules. And finally, we are going to look at LU decompositions. So we have about 4 subsections to cover in these modules. So we start with the first subsection, which is determinants by cofactor expansions. For a 2 by 2 matrix, given matrix A, where we have a 2 by 2 matrix, we can find the determinant of this matrix by simply using these equations, where we take coefficient A, we multiply with coefficient D, so we have AD, minus we take coefficient B, multiply with coefficient C. So if you solve that, then you get your determinants. And for a matrix A to be invertibles, we have a conditions where this equation is being met. So if we have this equation is equal to 0, so we have a matrix which is not invertibles. But if we have a values which is not equal to 0, so we have a matrix which is invertibles. For a larger size of a matrix, the concepts of minors and cofactors can be used. So these concepts I have explained in module 5, so you can go and check the module 5. We look at example 1, find the minors and cofactors of matrix A. Okay, so what is a minus? Minus is we assume we have a matrix M, which is stand for the metric of minus, where the coefficients of this matrix M is given by M11, which is referred to the positions of these coefficients, where it is located at the positions of row 1 and column 1. So if we have M12, we have a coefficient located at row 1 and column 2, and so on. Okay, so for this particular 3 by 3 matrix, we will have this matrix of minus. Okay, so once we have this matrix minus, we can find the cofactors. Okay, so the cofactors of A is given by these equations, where if we want to find the cofactors of A11, okay, so A11 means we find the cofactors of entries at row 1 and column 1. So we have A11. So you can use these equations where you have a negative 1 with a power of 1 plus 1. Okay, so why do you get this 1 plus 1 is referred to the positions of your cofactors. Multiply with your matrix of minus coefficient at 1, 1. So these ones will give you, so M11, to find the M11s, we cover row 1 and column 1. So you have this small matrix left in here, which is 5, 6, 4, and 8. So if you multiply that once, okay, if you find coefficient of this 2 by 2 matrix, you will get 5 times 8 minus with 4 times 6. Okay, so if you solve that, you will get a coefficient A11 equal to 16. So this is the cofactors of A at positions A11. Okay, so you can also find cofactors. Another way to look at the cofactors, if you still remember in module 5, to find cofactors, we multiply matrix of minus with matrix of sign pattern. Okay, so you can use that concept also to find the cofactor of of any matrix, okay? So the other method is we use the equations. Okay, so if we are using the equations, we can expand to find for another cofactors at different positions. For examples, if we want to find cofactors at A32. Okay, so what you can do is you take -1. So the power of -1 will be referred to the positions of coefficient 3, 2, which is 3 plus 2, multiply with metric of minus at position 3 plus 2. Okay, so this one, the power will give you 5. Okay, so it will become -1. So for the matrix 3, 2, it means if you cover row 3, okay, so let's say we erase that one first. So if you cover row 3 and you cover column 2, so what left is this 2 by 2 matrix. Okay, so 3 times 2 minus -4 times 6. So if you calculate that and multiply with -1, you get -26. So this is the coefficients of A32. With the concept of cofactors, we can expand, or we can use these concepts to find the determinant of matrix A. Okay, we look at these examples where you can see that we are using a cofactor expansions along the first row. So by using that, we can find the determinant of A. So given A as this matrix, we can choose any row. Okay, so let's say we're going to choose the first row, which is given by this one. So this is our first row. Okay, so we're going to apply cofactors in this row. So to get determinants A, so we can apply the concept of cofactors. Okay, so first we take this is the coefficients A11, so which is given by 3. So if you take 3s, then you cover this column 1 and row 1. So you have it a small 2 by 2 matrix, which you have this matrix. So next, you take at these coefficients. So you got 1. So when you cover that column 2 and row 1, so you have this small matrix 2 by 2 given by this. And finally, you take that 0 coefficients, and then you cover row 1 and column 1. So you have this 2 by 2 matrix given by this matrix. So you're left to assign the sign patterns of each of these coefficients. Okay, so you can use the concept matrix of sign patterns where for coefficient 3, okay, so let me erase that one first. For the coefficients 3, you have the position is 1, 1. So if you add them, they will give a positive sign. And for coefficient 1, you have the position for coefficient 1, which is row 1 and column 2. So if you add them, you got odd number, so it gives you a negative signs. And finally, for coefficient 0, you have a positions 1 and 3. So if you add them, you have an even number. So you can put a positive number here. Okay, so if you solve that, you get 3. So -4 times -2. minus 3 times 4 minus 1. So if you solve this, you get 3. Negative 4 minus 1, you get negative 11 plus 0. So that one will give you negative 1. So the determinant for this matrix is negative 1. So this is the determinant that we get when we only pick the first row, which is this row. So if you apply the same concepts, but you pick the second row, you should be able to get the same values, which is negative 1. And again, if you put the row 3, you should be able to get negative 1 as well. Okay, so this is a one way how you can find a determinant. So you can use a cofactor expansions along the row. So it can be the first, the second, or the third row. Okay, so next you can use cofactor expansions along a columns. Okay, so again you can choose the first columns or the second columns or the third columns. So you can apply the concepts for columns a part of row as well. Okay, so we try to apply determinants. Okay, cofactor. Sorry, we will apply a cofactor expansions along the first columns. So this is the first columns. So to find the determinant A, we apply cofactor expansions along the first column. So we have coefficient 3. Okay, so if you cover the row 1 and column 1, you get this small 2 by 2 matrix where you get negative 4, 4, 3, and negative 2. And then so you have negative 2 as your coefficients. And if you cover row 2 and column 1, so you get this 2 by 2 matrix. And finally, you take coefficient 5, and if you cover column 1 and row 3, you will get this matrix. Okay, so again, you need to find the sign pattern of each of these coefficients. Okay, so at coefficient 3, you have positions 1, 1, so this one will give you positive. At coefficient negative 2, you have a positions 1, 2, so it gives you negative. And at coefficient 5, you have a positions 1, 3, so it gives you a positive. So if you solve that, you get 3. Negative 4 times negative 2 minus 4 times 3. So that one become plus 2. So you have 1 multiply negative 2 minus 0 plus 5. 1 times 3 minus 0. So if you solve it, you get negative 4 plus 2. So that one gives you negative 2 plus 5, 3. And finally, if you solve it, you get negative 1. So that is this determinants. Okay, so you should be able to get negative 1 if you apply for column 2 and column 3. And if you compare this with cofactor expansions along the first row, you get the same value, which is negative 1. Okay, so in the other words, you can apply the concept of cofactor expansions, whether you want to choose for column or you can also choose for row. So next we move to another examples. So in these examples, we need to find the determinant of a matrix A, where we have a much slightly bigger matrix, where we have a 4 by 4 matrix. Okay, so in the previous examples, we know how to find determinants by using a cofactor expansions, either along row or column. So you can choose whether you want along row or columns. Okay, so to choose between these, either you want row or columns, there is a few way how you can choose it. Okay, so the easiest way how you can choose it is you choose a row or a columns that consists the most zeros. Okay, because when you have the most zeros, so it's, your calculations will become shorter. Okay, for examples, maybe we can apply or we can use cofactor expansions along the second columns. So this is the second columns where it consists a lot of zeros. So we take determinants A. Okay, so if you got 0, so everything will become zeros. Okay, so next you got 1. So if you covers column 2 and row 2, you will get this 3 by 3 matrix. So next, for the coefficients 0, you will get 0, and also for the other coefficient 0, you get 0. So it saves your time to do your calculations if you have a lot of zeros. And next, we assign the sign pattern. So for the coefficients 1, we have this at positions row 1, row 2, and column 2. So it will give us a positive. Okay, so we have 1, and then for the 3 by 3 matrix, we apply again the same concept, which is the cofactor expansions. And for this one, we choose the one with the most zeros, so we choose column 2. Okay, so for column 2, 0 and 0, we just ignore, so we choose -2. And if you choose -2, then it left you with a 2 by 2 matrix. Okay, so the 2 by 2 matrix will consist of this matrix. Okay, so the rest will be 0 because you have a coefficient zeros. So you can further simplify, or you can further put it in this form. Okay, so you reduce again this 2 by 2 matrix into a determinant. Okay, so how you do that, you take 1 multiply with 1 minus 2 multiply with -1. So you have this determinants where the way you solve it is you reduce, you pick which column that consists a lot of zeros, then you reduce the matrix from 4 by 4 to 3 by 3, 2 by 2, and finally you have the determinants. So if you solve these equations, you will get 2, and then these ones will give you 1 minus -2. So you got 2, 3, so you have 6. Okay, don't forget this is a -2, so that should be -2, and that should be -6. So your final answer will be -6. Okay, so that's how you choose which column or which row to perform your cofactor expansion. Choose the one that has the most zeros. Okay, so another useful way of evaluating a determinant is by following this pattern. But this pattern is only limited with a 2 by 2 matrix and 3 by 3 matrix. Okay, so for example, if you have a 2 by 2 matrix, you have this coefficient A11 until coefficient A22. So how can you apply for a 2 by 2 matrix? Is just as usual. So this one is given in the theorems, okay? So you can take the coefficients A11 multiply with coefficient A22, and then minus with coefficient A12 multiply with coefficient 4, so you got determinants. But if you have a 3 by 3 matrix, so what you can do is you write back this 3 by 3 matrix, okay? And then you go back to your first columns, you write the first columns 1 to become as a column 4, and column 5 is taken from your column 2. Okay, so in the other words, you just copy the first two columns, you put it on the right-hand side. And then you multiply, then you can indicate the flow of these equations or the flow of these coefficients by these arrows. Okay, so you have the flow of arrows going down and going down to the right-hand side and going down to the left-hand side. So for this part, you have the arrows going down that side, and for that part, you have the arrows going down that side. Okay, so if you subtract these two, you get negative. You get 240. So that is your coefficient. So next we move to the next subsections, where in these subsections we're going to find determinants using row reductions. So this method is to reduce the given matrix to upper triangular matrix form by row reduction. So this is the elimination method. So let's say we have this example 1 where we need to find the determinant of matrix A. So the goals of our solution is we want to change or to reduce this matrix A to become an upper triangular matrix where the diagonal line will consist of 1, 1, 1, which is the identity. And for the upper triangular matrix, you have this to be any values on the upper right side of the matrix, and for the lower left side of the matrix, you have it become 0. Okay, so this is the form that we want to reduce before we find the determinant of this matrix. Okay, to get this into this kind of forms, or the upper triangular forms with this diagonal coefficient consists of 1, we need to perform eliminations method. Okay, so we can start with the first entries here at position 1, 1. Since we have zeros, we need to convert it into 1. So we can use a swap between different rows. So if that is row 1, row 2, and row 3, we can swap row 1 and row 2. So it becomes, for the row 1, for the row 2. So you can see here that we already swap it. And for the row 3, we just write back. Okay, so we have a 3. So with 3, we can change it to become 1 by simply we take row 1 multiply with 1 over 3. So we have these coefficients. For the row 2, just write it back, and for the row 3, just write it back. Okay, so next we move to the next coefficient. 0 is fine, and negative 2, we need to change it to become 0. So to change 2 to become 0, so we can take row 3 plus with row 1, but we need to multiply row 1 with negative 2. So that will give us these coefficients. For the row 2, just write it back, and for the row 1, just write it back. Okay, so next we move to the next coefficient, which is negative 2 is fine, 1 is fine, but 10 we need to change it to become 0. So to do that, we take row 3, we plus with row 2, but we need to multiply row 2 with negative 10. So that will give us these coefficients. And for the row 2, just write it back, and row 1, just write it back. And finally, we need to change this coefficient negative 55 to become 1. So to do that, we take row 3, we multiply with 1 over negative 55. So we have 0, 0, 1. And for the row 2, just write it back. And for the row 1, just write it back. Okay, so next, once we get this in a form of a triangular matrix or in an upper triangular matrix, then we can find the determinants of our matrix A. So how to find the determinants? You look at these coefficients that involved with this diagonal matrix. Okay, so the first ones, you have this 1 over negative 55, okay? So that ones we need to use to change to get this coefficient 1. So you take that negative 55, multiply with, for the other coefficient, which is that ones, okay? So what values do you need to convert that to become 1? You didn't use any values, okay? So you just write it as a 1. So next, we move to that coefficient 1, okay? So to get that to become 1, so what operation that involved is this one, isn't it? Because at first you get 3, but to change it to become 1, this operation is needed, which is 1 over 3. So you just take the 3 to multiply as a determinant. So that one will give you 165. All right? So when you find a determinant, you just focus on the diagonal elements of your coefficients. And the operation that involved to get these diagonal elements, okay, so is what we will use as our coefficients in finding our determinants. But that coefficients will be, if you have in terms of ratio, which is 1 over negative 55, you just take the one that down there. Okay, so this is the denominator. Okay, so if it didn't involve with any scalars, okay, multiply by scalar, so you just multiply by 1. Okay, so finally you have these equations. Oh yeah, one more thing I forgot to mention. When you swap the row, like in the first steps, when you swap the row, because you swap the row 1 and row 2, in order to change 0 to become some values, so you need to swap the row. So when you swap the row, the coefficients that involved in here will become negative 1s. So in the other words, when you find the determinants, you need to consider this swapping method where it can be indicated as negative. So in that case, when we find our determinants, okay, so just now we just write 3, but before we get this 3, we need to swap because it starts with a 0 values. So because of that, we need to multiply with negative 1. So in here, you're supposed to have a negative. In the end, you get this positive 165 as the determinants. Okay, so don't forget that one. If you swap a row, you need to multiply with a negative inside your determinants. Okay, so next we look at example 2. So in these examples, we need to find the determinant of a matrix A. So another way to solve this matrix is we change this matrix A into the lower triangular forms. Okay, so just now we change a matrix into an upper triangular form. So you can also change the matrix into a lower triangular form before you find the determinant of that following matrix. Okay, so our goals in here, we want to change this into a lower triangular form where the diagonal line consists of 1. Okay, so it's up here, we have a 0. And down here, we can have any numbers. Okay, so this is the form that we want to change where this is a lower triangular form with the diagonal line consists of Okay, so the first things you can do a row operations or a column operations. Again, in here, we're going to make it a bit slightly different. Okay, usually we use or we perform elimination method based on row, but you can also perform elimination method based on column. Okay, so we start with the first coefficient 1, so that is fine. Okay, so down here is fine. So if we want to change into our target forms, we can start with this coefficient 3. Okay, so we will do the elimination method based on column. So if that is our column 1, this will be our column 2, column 3, and column 4. Okay, so our target is we want to change this 3 to become coefficient zeros by eliminating based on columns. Okay, so to change that to become 0, we take column 4, we plus with column 1, but we need to multiply column 1 with negative 3. So that one will give us these coefficients. So for the column 3, 2, and 1, we just write back the coefficients since we didn't perform any operations. So we have this matrix forms. Okay, so if you can see here, okay, so we already have this in a forms of lower triangular matrix. Okay, so the only thing that we need to make this diagonal line to become 1. Okay, so to do that, we start with this row 2 first. Okay, so in order to get 7 to become 1, we need to multiply by 1 over 7. For the row 2, for the row 3, in order to make 3 become 1, we multiply row 3 with 1 over 3. And for the row 4, in order to get this negative 26 to become 1, we multiply with negative 1 over 26. And for the row 1 is fine because we already get 1. Okay, so remember, when we find the determinant, we need, so the coefficient that we need to write in this determinant is the one that we need, is the operation that involve when we want to change this diagonals coefficient to become 1. So we have 3 operation in here. In fact, we have 1 operation in here. So this one's for the row 1, since we didn't change anything, so we just write as a 1, multiply with, for the second row, we multiply with the denominator 7. And for the row 3, we multiply with denominator 3. And for the row 4, we multiply with denominator negative 26. Okay, so that would be inside our determinant operations. So if you solve that, we get negative 5, 4, 6. Okay, so since you didn't involve any swap between row or column, so you don't need to multiply with negative 1. Okay, so next we move to example 3. So in these examples, we have a 4 by 4 matrix. So we need to find the determinant of this following matrix. Okay, so recap back what we have learned. In order to find a determinant, you can use two methods. The first one is cofactor expansions. Okay, so you can choose this either by row or by column. So to save some time when we're finding a determinant using cofactor expansions, we choose row or column that consists many zeros. So otherwise, you can choose any row or columns if you don't have a lot of coefficients with zeros. And secondly, we can find determinants by using row reductions method. Okay, so this is elimination method. Again, you can perform your elimination method by row or by column as well, but you need to have a target, or you need to have a particular forms. So the first form is you can reduce your matrix into a upper triangular matrix, or the secondly, you can reduce to a lower triangular matrix. Okay, but in this both of these matrix, your diagonal line must be one. Okay, so in other words, your diagonal elements must be one. So before you can perform the determinant operations. Okay, so I want you to try this by yourself. So you can choose either you want to use cofactor expansions or you want to use row reductions. And when you solve it in the end, your determinants will be equal to negative 18. Okay, so you can try this. Okay, so next we move to the next subsections where we're going to look at the Cramer's rules. Okay, so what is a Cramer rule? So it's another method that we can use to solve a system of linear. Okay, so consider we have A, X equal to B. Okay, so this is a system of linear equations where A is consists of a matrix, X consists of a matrix, and B consists of a matrix. Okay, but this matrix is actually come from more than one linear equations. Okay, so you can read these theorems, but we straight away jump to the examples. Okay, so based on these equations, or based on these theorems, we can somehow solve this equation. So let's say our A, okay, so let's say this is Ax equal to B. So our matrix A will be consist of coefficients. Let's say this is x1, x2, and x3. So A will be equal to this matrix. Okay, so for the AX1, we need to come up a matrix for AX1. So matrix AX1, we simply take x1, okay, the coefficient inside x1, column x1, we replace with B. So we have this matrix. For AX2, we replace column 2 because column 2 is where your x2 comes from with this matrix B. So we have and finally for matrix AX3, we replace entries in column X3 with entries B. So we have these forms. Okay, so therefore, to find x1, we simply use these equations where we find determinant A1 divided by determinant A. And for x2, we get determinant AX2. Okay, so this is AX1 divide with determinant A. And finally, for x3, we get determinant AX3 divide with determinant A. Okay, so you need to find determinant of all these matrices. Okay, so if you find the determinant, again, you can use what I have explained just now. You can use cofactor expansions, or you can use row reductions. But once you find it, then you can put the value in here. For x1, you will get negative 10. Sorry, you will get negative 40 divided by 44. Okay, so this one, if you want to simplify, you can also simplify. For x2, you will get 72 divided by 44. And for x3, you will get 152 divided by 44. Okay, so that means for the determinant A is equal to 44. For determinant AX3 is equal to 152. Determinant AX1 equal to negative 40. And finally, determinant AX2 equal to 72. Okay. So this is another way to solve a system of linear equations. Okay, so in this modules, we mix a bit with a system of linear equations. All right, so another way to solve a system of linear equations, we can use LU decompositions. So suppose that we have a system of linear equations where it is described by AX equal to B. So the matrix A we can decompose into two different matrices where it was in the form of L, which is stand for lower triangular matrix, and a form of U, which is stand of a upper triangular matrix. So our aim is to find L and U, and once we have done that, we will be able to found our decompositions. So this is another way or another approach to solve system of linear. And one more thing, an invertible matrix A has a LU decomposition provided that all its leading submatrices have non-zero determinants. So what this means is if we have let's say we have a 3 by 3 matrix, so we need to find the determinants of all these matrices, which is start from 1 by 1 to 2 by 2 and 3 by 3. This is called as a leading submatrices. So if we find the determinant of 1 by 1 matrix, we got 1. And for a 2 by 2 matrix, we got determinant 2. And for 3 by 3 matrix, we get determinant 6. Okay, so we don't have any zeros determinants. So because of that, this matrix A can be decomposed into L and U matrices. Okay, not all matrices can be decomposed into LU decomposition. If that matrix consists of determinant 0, then we cannot decompose into LU decompositions. So now we look at examples. So consider we have these problems where we can express this in terms of a system of linear equations where we have AX equal to B. So A can be written as LU X equal to B. So we need to find what is our L and what is our U. So we start from a matrix A. So our aim is to reduce this matrix into an upper triangular or lower triangular matrix. So we have the following matrix forms where the diagonal line consists of 1. Okay, so you can choose whether you want to reduce A to become as in the form 1, which is upper triangular matrix, or in the form of 2, which is lower triangular matrix. Okay, so let's say we choose A to be reduced to become in a form of upper triangular matrix. Okay, so we can start with the first coefficient, which is 2. So that one would be row 1, row 2, row 3, row 4, row 5, row 6, row 7, row 8, row 9, row 10, row 11, row 12, row 13, row 14, row 15, row 16, row 17, row 18, row 19, row 20, row 21, row 22, row 23, row 24, row 25, row 26, row 27, row 28, row 29, row 30, row 31, row 32, row 33, row 34, row 35, row 36, row 37, row 38, row 39, row 40, row 41, row 42, row 43, row 44, row 45, row 46, row 47, row 48, row 49, row 50, row 51, row 52, row 53, row 54, row 55, row 56, row 57, row 58, row 59, row 60, row 61, row 62, row 63, row 64, row 65, row 66, row 67, row 68, row 69, row 70, row 71, row 72, row 73, row 74, row and row 3. So to get coefficient 2 to become 1 as what we want in here, so we take row 1, we multiply with 1 over 2. So we get these coefficients. So for the row 3 and row 2, we can just write back the coefficient because we didn't change or we didn't do any operations. So let's introduce another matrix which is called as the elementary matrix. Okay, so the elementary matrix E will have a standard form of an identity matrix where you have a diagonal elements consists of 1 and the rest of the elements consist of zeros. Okay, so for the first elementary matrix, it will be described by the positions that we have changed just now, which is this one. So we have elementary matrix at position 1, 1 is equal to, okay, so what is changed in here is your positions 1, 1 here. Okay, so you need to replace this coefficient position 1, 1 with the one that you use in your operations. So for this case, the one that you use to change it to become 1 is 1 over 2. So the rest of the coefficients would not change. Okay, so this is reflects during your first operations. So for your next operations, okay, you want to change -3 to become 0, okay, to become 0 like this. So in order to change that to become 0, so at row 2, you can add with row 1, but you need to multiply with 3. So that one will give you 0, 1, and 3. So the rest of the coefficient, you can just write it back. Okay, so next we move to our elementary matrix. So what changed in the elementary matrix is in this position, which is indicated by 2, 1, which is row 2, column 1. Okay, so where is row 2, column 1 is in here. Okay, so what do you write here is you write 3 because you use 3 in the operations. So the rest of the coefficients will be following with your standard form of elementary. So next, we move to 4, coefficient 4. So we want to change coefficient 4 to become 0. So what operations you need is you take row 3, you plus with row 1, but you need to multiply row 1 with -4. So that will give you these coefficients. So for the row 2, you just write it back. And for these operations, you need to find the elementary matrix as well. So the elementary matrix will be in these positions. Okay, so which is at row 3 and column 1. Okay, so position row 3 and column 1 is in here. So what should you write here is this scalar in the operation, which is -4. So the rest of the coefficients, you can just follow the standard form, which is given up here. Okay, so next we move. Okay, so again, our target is we want to change this matrix A to become as in the form number one, which is upper triangular matrix. Okay, so the next coefficients would be these coefficients. So we want to change it to become 0. So to change that to become 0, we take row 3, we plus with row 2, but row 2 must be multiplied with positive 3. So that will give you these coefficients. So the rest of the coefficient in row 2, just write it back, and row 1, just write it back. So these operations will give you elementary matrix at positions. So that positions is referred to row 3, column 2. Okay, so which is located here. Okay, so what number should you put here? You put this operation that have 3. So the rest of this coefficient in this metric, you just follow the standard coefficient because you didn't do any operations. Okay, so finally, you change the 7th to become a 1. Okay, so by changing that to become a 1, you will have a complete lower triangular matrix form. So to change that, we take row 3 multiply with 1 over 7. So that one will give you these coefficients. For the row 2, just write it back, and for the row 1, just write it back. And as for the elementary matrix at this particular position, which is at position row 3 and column 3, so you need to change the coefficients to become 1 over 7. Okay, so the rest, you just write it back according to the standard forms. Okay, so this one is what you call as your U. Okay, so it's the upper triangular matrix. So your A consists of U, which is this one, okay, and L. So what is the L? Okay, so before we find what is the L, we look at further on our elementary matrix. Okay, so we have this elementary matrix. Again, so you need to do this elementary matrix based on the operations that you get when you perform the elimination method. Okay, so we start with the elementary matrix 1, 1. Okay, so we need to find the inverse of this. So if we find the inverse of elementary matrix 1, 1, so what we get is we just simply, okay, change this from 1 over 2 to become 2 because we just moved to up. So it's become 2, 0, 0, 0, 1, 0, 0, 0, 1. Okay, so you can see only this particular matrix that change form. The rest of the matrix not change form. Okay, so we do that for the rest of this elementary matrix. Okay, so which one that change form is 3 will change to become negative 3. So the rest of the coefficient will remain the same. And for E31, if we take the inverse, okay, so what change is this negative 4, okay? So negative 4 will become 4. The rest of the equation, the rest of the coefficient will remain the same. And for the E32, Okay, we take inverse. So only these 3 change become -3. So the rest of the coefficient remain the same. And finally, for the E33, if we take the inverse, only the one that located at position 33 change from 1/7 to become 7. So the rest of these coefficients will remain the same. Okay, so you can see the pattern here. If you have a positive numbers, it become negative if you take the inverse of it. And if you have a fraction number, okay, like 1/7, it will become a non-fraction number which becomes 7. Okay, so I hope you can see the pattern there. So finally, once you do that, then you can find your L matrix. So your L matrix is given as the multiplications of all these elementary inverse matrix, which is we have E11, -1, E21, -1, E31, -1, okay? So your L in here is the product of all these inverse elementary matrix. So if you multiply that, okay, so you will get, let me write it here. Okay, so you will get your L is equal to 200, -3, 10, 4, -37. Okay, so how do you get this? It's quite simple. Okay, so you look at this coefficient in each of these elementary matrix. Okay, so you got 1, 0, 0. So for the first row, you got 1, 0, 0, 1, 0, 0, 1, 0, 0. Okay, and you got 2, 0, 0. Okay, so 1, 0, 0 is the standard forms. The only one that changed is these two. Okay, so that's why when you multiply, it's only this is change. In the other words, you just write back the one that changing, okay, the coefficient that changes. The rest of the coefficient that not change, you just remain the same. Okay, so for like E21 is the one that change is -3. Okay, so that one will be reflect in your final multiplications, and 4 and -3 and 7. Okay, so you can see here 2, -3, 4, -3, and 7. Okay, so this one is you get by you combining all these inverse elementary products, where you have 7 in here, -3 in here, and 4 in that, -3 in these coefficients, and finally you got 2 in that coefficients. Okay, so you just combine into a single matrix. So that would be your L matrix. So your U matrix will be in these forms. So when we have, so our matrix A just now can be decomposed into U and L matrices. So L is given by this values, and U is given by that values. Okay, so if you start with U, your elementary matrix will end up become L. But if you start with L, your elementary matrix will end up to become U. So once a matrix A has been decomposed into lower and upper triangular parts, then we can start find the solutions for this system of linear equations. So just now we have the following problems. So we have decomposed this matrix A to have decompositions of L and U, which is described by these forms. Okay, so this is our L and this is our U. So this is our problems. So we can solve that by this following method. Okay, so firstly, before we solve for X, we need to first solve for y. Okay, so what is y? We consider we have a matrix L multiplied with y equal to a matrix B. So the matrix B is given by this following matrix, where this is your A, this is your X, and this is your B. So your L would be 2, 0, 0. This is your L, and your Y would be y1, y2, y3. And your B would be 2, 2, 3. Okay, so before you solve for X, you need to solve for Y. So what is Y? Y is unknown parameters that come with these forms. Okay, so from here, you can come up with these particular equations where 2 multiply y1 is equal to 2. So if you solve it, you got y1 equal to 1. So the second equation, negative 3y1 plus y2 equal to 2. So if you solve it, you got y2 equal to 2 plus 3y1, which is 1. So it gives you the value of 5. And for the equation 3, you have 4y1 minus 3y2 plus 7y3. So if you solve for y3, you will be able to get 2. So your matrix Y will be consist of y1 is 1, y2 5, and y3 is 2. So this is your matrix Y. So finally, you can solve for X, where you have this particular form Ux equal to Y. Okay, so it's not equal to B anymore. So we take U is this matrix, and we multiply with X, where X is X1, X2, and X3. So it's equal to Y, which is 1, 5, and 2. So if we solve this, we get the first equations as follows. The second equations as follow, and finally the third equations. So if you solve these three equations, you will get x1 so these ones you can write it also as 2, negative 1, and 2. Okay, so this is the answers for your system of linear equations. So that's all for this module. So if you have any problems with this module, you can just let me know. And then if you need discussions, you can also request for maybe a live discussions. All right.